Hello, everyone. Thank you so much for joining us today to learn more about Cloudwatch Container Insights. I am Sadipta Jyoti Prakash, Principal Product Manager with the Amazon Cloudwatch team, and today we'll learn more about the support of Prometheus metrics on Container Insights. To start off with the agenda, we will briefly discuss the diagnostic needs of microservices-based environments, followed by a quick overview of Container Insights and Prometheus integrations. We will learn more about the updates to Container Insights, and finally, we will talk you through some of the demo and how it works. Let's start with the diagnostic needs that we commonly hear from our customers of applications based on microservice-based environments. There are three key areas that we identified. The first is distributed architectures are becoming more bespoke and complex, where DevOps engineers are increasingly looking for a bird's eye view of the application and understand its components. They need to easily locate and isolate sources of issues by zooming in into individual components or workloads. While they investigate further, they need to derive insights from the data collected across the resources and connect the dots between, for example, the errors in metrics and logs. To further elaborate, today, customers run their business-facing application on orchestration engines such as Amazon Elastic Container Service, which is ECS, AWS Fargate, Amazon Elastic Kubernetes Service, which is EKS, and Kubernetes based on EC2. Customers can use a variety of agents such as the Cloudwatch agent, the Prometheus agent, the X-ray and OpenTelemetry agents to monitor their applications on Cloudwatch using the core business observability pillars that are metrics, logs, and traces. Bringing this back to Container Insights, here we provide a set of pre-built and automated dashboards with resource map, alarms, and all the Cloudwatch goodies to enable customers to better monitor your applications. Here's a view of Container Insights and the set of key metrics and telemetry we collect. However, many customers provided us feedback that they would like further visibility into their workloads that run on their applications. With this in mind, we explored popular sources of data that customers wanted to collect, many of which you might have already heard of, and also have heard of Prometheus, a popular open source monitoring tool that is led by the CNCF project with a large and active community base of practitioners. We heard from customers that they wanted to monitor workloads such as HAProxy, Memcache, and Nginx, and many more. Bringing it all together, we now support the monitoring workloads and such metrics on Container Insights using Prometheus endpoints available both on ECS and Kubernetes-based environments. So what's new? This new release automatically collects, filters, and aggregates Cloudwatch metrics from your workloads. You can utilize pre-selected services that are scraped and automatically enriched with metadata such as cluster and pod names. This release supports scraping of 150 plus open source third-party exporters compatible with open metrics. We also support custom metric scraping on services to ingest the Cloudwatch metrics. For example, you can now collect application metrics from your namespaces. You can start by running the Cloudwatch agent on the Kubernetes cluster. The agent supports Prometheus configurations, discovery, and publishing all the high-fidelity Prometheus metrics and metadata. As mentioned earlier, custom metrics available for curated sets of dimensions that are fully configurable are available with this release. Publishing aggregated Prometheus metrics as Cloudwatch custom metric statistics reduces the number of metrics needed to monitor, alarm, and troubleshoot the performance and failures, enabling you to simplify your monitoring experience. Finally, you can analyze the high-fidelity Prometheus metrics using Cloudwatch Logs Insights query language to isolate specific pods and labels impacting the performance of your containerized environments. Here's an example of an EKS cluster as a runtime environment configured with the Cloudwatch agent for ingesting Prometheus metrics as EMF events into Cloudwatch. We use the Nginx as an ingress configurator as a scraping target. There's a demo app generating traffic, and we have three namespaces in the EKS cluster. That is the Amazon Cloudwatch, which hosts the Cloudwatch Prometheus agent, the Nginx ingress sample, where we have an Nginx ingress controller running, and the Nginx sample traffic, which hosts the sample app, including the traffic generator. The traffic generator makes some HTTP calls routed through the Nginx ingress, and the Nginx ingress controller exposes the statistics from these HTTP calls as Prometheus metrics, and these are finally flushed into Cloudwatch container insights through the Cloudwatch agent enabled with Prometheus. Now let's switch to demo mode and view this in action. Here we are with the Cloudwatch console homepage, where you can see alarms by the AWS services, along with the recent alarms that have been triggered within your account. The services essentially show X-ray having one of the alarms, while an app mesh which has been set up with anomaly detection enabled on it. This particular account has a pet adoption demo website. This is what I'm sort of quickly walking you through. All the clicks on this website are microservice-based environments. And we have also created a default dashboard that looks at some of the logs generated along with Envoy downstream HTTP information. Let me quickly navigate to Service Lens, which is enabling you to help visualize all the various transactions that go through your particular application. Here, it's the pet adoption website. You can see all the various components, which are either Lambda function, databases, microservices, such as containerized environment. For example, here's the pet search API on which once you hover, you're able to visualize some of the key telemetry associated with with that particular cluster. I'm now navigating to the Cloudwatch Container Insights console from the homepage. Here, the automatic dashboards are preloading for the EKS cluster, which I could go ahead and visualize the various clusters available, filter down into various nodes that I would like to focus on, or even look at the various other IP segments that I'm interested in further. All of this was part of the Container Insights previous version, where you were able to sort by CPU and memory and look at the pods in order to focus on areas that might be causing issues within your application. However, we launched a new updated version of Container Insights that's available on the left navigation, which provides a similar experience under the Performance Monitoring tab. If you navigate to this particular view, you can see similar EKS cluster automatic dashboards, along with other similar dashboards for namespaces, where, for example, you can see now the pet site and the associated pod performance for this particular namespace. All the metrics that have been collected are readily visualized within the predefined dashboard. We also launched the resource view, which is essentially a list view of all the various clusters, tasks, namespaces that you might have, which is simple for you to filter out if you're interested in a specific component. You can also sort by CPU or memory in order to look at what are some of the areas that have the highest issues within your application, and you can focus on, let's say, the cluster pet site right here, which is causing more issues. And if you click on this, it basically takes you to the performance monitoring dashboard that you saw previously. We also have the alarms that are mentioned below, which essentially gives you a summary of what might be going wrong across your resources. And within these, you can also focus your attention on, let's say, the app mesh, which looks fine right now, but it might be going into issues at a later point of time. Another aspect that customers gave us feedback on is while list view is important, they would like to also understand the dependencies between the various aspects within their application. So we've built the map view, which essentially shows you the dependencies between the cluster, the namespaces, the pods, and so on. Here in the demo app, you can see the various EKS and ECS segments and the dependency map across, for example, the workloads such as Nginx, HA proxy, which were all available as part of this demo. You can also hover over them, very similar to the experience in Service Lens, where you can get CPU, memory, and some of the network metrics just as a quick glance as such. If in case you would like to do some further investigation, you can narrow the scope of the map down to a specific cluster or a node, or you can view a subtree, which helps you further narrow down an area of interest and diagnose in the context of time as well. Here, I'm also showing you the two different modes, which is the CPU mode and the memory mode, where you can essentially narrow down such large maps into segments that require most of your interest. Here, I've moved to the CPU mode where we have highlighted a couple of service names which are in red, which is essentially telling you that their CPU utilization is higher than the rest of the components on your map, enabling you to easily focus on areas which might be currently facing issues as such. Here, now that I've zoomed into the CPU mode, I'm able to see more about the statistics on the particular service name as such. I can also switch to memory mode to see what are some of the memory metrics compared to the rest of the map. Seems like memory seems to be less of a problem than the CPU utilization. I'm just hovering across my overall map to see if there is any other areas that are facing similar issues. Seems like this is the only cluster where we are facing high CPU utilization. I'm opening up this draw to actually see the data in the context of time. 55% right now might be acceptable, but has this been consistent or not? You're able to quickly visualize it in this current draw where you're able to focus on the three key metrics that we are focusing on, which are CPU, memory, and the network metrics as such. Here I'm focusing on the Nginx ingress, which was part of the previous highlight that I gave regarding the setup as such. You can see that the Nginx metrics is where you've been collecting the controller metrics, and I can quickly jump to the predefined dashboard associated with this particular Nginx. You can also see the Nginx service, the pod that's running on it, the controller connections, and other metrics that we've been collecting from this Nginx endpoint. I can also switch to the Memcache predefined dashboard or app mesh. These are all automatically discovered as and when you've set up your Prometheus endpoints. For example, now that I've jumped to the app mesh dashboard, you can see I have 5 pods which have an uptime of 2.53K. You can see the total inbound and outbound traffic if there are any jitters along that way, and the upstream errors if there are any that are occurring. You can also visualize all of this data as your own dashboard by clicking on Add to Dashboard and updating any of the widgets if you intend to learn more. Now going back to the service map of Service Lens, I would like to quickly show you that all of these essentially are connected. So you can quickly click on one of the nodes on your application and click on Container Insights in order to be directed towards the containerized visualizations, which help you focus on the areas within the map that are connected to your overall application, helping you simplify the relationships between metrics, logs, and traces as such. So here we were jumped from the Cloudwatch service map to the map view within Container Insights, and I'm able to visualize the various components in order to further dive deep into any pod-related, cluster-related issues that you might be facing. And this was a quick summary of all the new updates that we've done to Container Insights in order to help you monitor your microservices better. I'd love to now turn it over to my colleague Vijay, who will help you look at some of the ways in which you can use custom metrics from these Prometheus endpoints in order to help you with the auto-scaling of containerized environments. Over to you, Vijay.
Thank you, Sudipta. Hello, everyone. My name is Vijay Sarathi. I am a Senior Solutions Architect at AWS. Today, I am going to show you a demo of how we can use the Cloudwatch agent for Prometheus in conjunction with Cloudwatch metric alarms to auto-scale a microservice deployed in Amazon EKS based on a custom Prometheus metric. What I have here is a Java-based microservice that I call the Recommender app that is deployed on an EKS cluster. And the service has been deployed to the cluster as a replica set with 2 pods. And the service also exposes a set of REST API endpoints to get recommendations of popular products for an e-commerce website. And this application has also been instrumented with Prometheus client library, and it uses a Prometheus counter named HTTP request total to track the number of HTTP requests that are made to its endpoints. And the data, this metrics data is exposed at the endpoint name /metrics so that scrapers like Cloudwatch agent for Prometheus can gather metrics from the service. And our objective is to scale this service when the rate of HTTP requests exceeds a given threshold. To do that, what I have done is I've deployed the Cloudwatch agent for Prometheus in my cluster. We'll go to the editor and look at how it has been configured. So the Cloudwatch agent contains 2 sets of configurations, both provided through Kubernetes config map. The first config map contains standard Prometheus scrape configuration that determine the set of microservices from which the agent scrapes metrics. In this case, the agent has been configured to scrape the metrics only from pods in the Java namespace. The second set of configuration, which is seen here, shows configures how Prometheus metrics collected by the agent are converted into performance log events with EMF. So in this case, the agent has been configured to emit logs that pertain only to the metric named HTTP request total and matching a given set of labels. Now, with these configurations and deployments in place, I can now see the performance log events under Cloudwatch logs, and this is what a typical log event looks like. It'll contain all the labels associated with the Prometheus custom metric, plus the EMF data under the Cloudwatch metrics field of the JSON object. And using this EMF, Cloudwatch Container Insights will extract metrics data out of the log events. So we can now visualize this data in the metrics dashboard. I have been generating a steady load of HTTP requests against my service using Postman running in the background. So here I am plotting both the original metric counter named HTTP request total that was scraped from the service, as well as a derived metric named rate HTTP request total that was computed from the original metric using metric math expressions. And as I mentioned before, our objective is to scale the service when this derived metric breaches a given threshold. So how do we do that? We need to create a Cloudwatch metric alarm that watches this metric over a specified time period and triggers an action when the metric breaches a set threshold. And we're going to do that in a Kubernetes native fashion by first deploying a custom controller. This file operator.yaml deploys a custom controller into this kube system namespace. And here is the custom controller pod. And I'm going to set the pod variable. And then I'm going to look at the logs of this custom controller. So when it starts up, all that it is doing is basically it's going into a wait state, and it is waiting for the API server to send notifications. And these notifications pertain to whether a custom resource has been created in the Kubernetes the cluster. Now, next we will take a look at let's take a quick look at the actual operator.yaml and what all it contains. So first and foremost, this operator YAML file contains a custom resource definition, which defines a schema for the custom resource called K8s metric alarm. And then it also has some RBAC artifacts such as cluster role and cluster role binding. And then the custom controller itself is actually deployed as a Kubernetes deployment with one replica. Now let's take a look at an instance of a custom resource. So here we have an instance called HTTP request rate, which matches that custom resource definition called K8s metric alarm. Let's first deploy this and then come back and take a closer look at what all it contains. So I'm going to do kubectl apply -f on HTTP request rate alarm. So when I run this command, and you can see that the custom controller immediately springs into action because it was notified by the API server that this custom resource was created. And it went ahead and created this Cloudwatch metric alarm called HTTP request rate high alarm. Now, if we go to the Cloudwatch alarm dashboard, we should see this alarm show up here. Okay, I can now see that when I drill down into this alarm, I see the metric data that is being watched by the alarm, which is indicated by the orange line. And this shows that we have a steady load of about 8 requests per second. And we also see the red line, solid line, which is indicating that the threshold has been set at 5 requests per second. Now let's go back and look at what all information is contained in the Kubernetes custom resource that we use to create this alarm. First and foremost, it has the complete JSON definition of a Cloudwatch metric alarm. This is the exact same JSON data that you would use if you want to create a metric alarm using AWS CLI. The metric name and the dimensions seen here, they correspond to the custom Prometheus metric that was scraped from the microservice by the agent. And this alarm is set to trigger when the metric breaches the threshold for 2 out of 3 periods. Each period in this case is 1 minute. And at the top, it also contains configurations that identify which particular Kubernetes deployment is the target of the scaling action. And it has parameters that control the scaling velocity, as well as the minimum and the maximum number of parts that are resulting from the scaling action. Now let us go back to the Cloudwatch alarms dashboard. And because the metric value has been trending way over the set threshold, by this time that the alarm should have been triggered and a scaling action should have taken place. And when the alarm gets triggered, what it does is it sends a notification to this SNS topic called Cloudwatch alarm topic, which I have in this next tab. And this SNS topic, there is a Lambda function called Cloudwatch alarm handler that is subscribing to this SNS topic. So what happens is when the alarm triggers, the Lambda executes, and when the Lambda function, it receives the SNS event that it receives, it has all the information that it needs to find out which is the alarm that got triggered and what is the target deployment in the Kubernetes cluster. It has all that information. So all it does is basically it acts as a simple Kubernetes client and performs a scale-out action by talking to the Kubernetes API server. So when we look at the logs for this Lambda function, we should now see that at the very top, when the Lambda function started executing, we initially started off with 2 parts, and then based on the configurations in the custom resource, it was scaled from 2 to 5 parts, and that's because the custom resource definition in the scaling behavior, we said scale by either 3 parts or 50% of the number of parts, or whichever is higher. So if I go back to my console and then look at the number of parts in the Java namespace, I initially had 2, and I have 5 parts that are running now. So this is how you use the Cloudwatch agent for Prometheus in conjunction with Cloudwatch metric alarms to scale a microservice that is running in Amazon EKS. And this procedure is applicable equally to services that are running in self-managed Kubernetes clusters running on AWS. That concludes this demo.
In summary, we'd like to speak about the few tools that help you with your diagnostic needs of microservice-based environments. First, in order to understand distributed architecture, you can now use the resource view with map and list to organize containerized resources. You can zoom into individual components, narrow down to specific namespaces, services, and pods to zoom into issues. And finally, you can derive insights from collected data and connect the dots across metrics, logs that are collected from your containerized environments. Once again, thank you so much for joining us today and learning more about container insights. Please complete the survey at the end of this session for helping us learn better. Thank you.